This is Introduction to Covalent Bonding. There are two types of compounds or bonds. The first type we have already learned about, and that is ionic bonding. This means that we have a metal and a nonmetal coming together. So the metal is a cation, the nonmetal is an anion. The cation gives up a valence electron to the anion so that both atoms meet the octet rule. This results in a positive-negative charge causing electrostatic attraction and bonding. So let's take a look at an example. Sodium chloride. So we have Na. Let me turn my pen on first. We have Na, and sodium has one valence electron, so we would just put one dot. Then we've got chlorine. Chlorine has 7 valence electrons because it's in the 17th group. Chlorine needs one more electron to meet a full octet. So the compound that we form is we have a sodium cation, and then next to it is a chlorine anion. The attraction between the positive and the negative charges is the ionic bond. So we've done that. You've learned how to name compounds. Now we're going to be moving on to covalent bonding. This is found in molecules. So covalent bonding, these are composed of 2 or more nonmetals. In this case, atoms share pairs of valence electrons to fulfill the octet rule. Examples of sharing one pair of electrons these are all single bonds, okay? So they're sharing a single pair of electrons. I'm going to keep saying the word pair. You're going to get really tired of seeing it. So what I have over here on the drawing is a hydrogen atom with one lonely electron. The 2 hydrogen atoms are going to approach each other, and notice that they're sharing the electrons right here. So this is the covalent bond. The electrons are attracted to the nuclei of both atoms. So let's write this: electrons attracted to both nuclei. Let's do some examples. Let's take a look at hydrogen. And then we're going to have a second hydrogen. All right. They both would like to meet the octet rule. And in the case of hydrogen, they meet the duet rule because you can't have more than 2 electrons in the 1s orbital. So the 2 of them are going to come together to form the H2 molecule. And we're going to do a Venn diagram. I don't know if you remember these from math, but if we do that, we can see that both hydrogen atoms get to count the shared electrons as part of their valence electrons. So each atom meets the octet rule. Let's take a look at fluorine, another one of your diatomics. So we've got fluorine, and that has 7 valence electrons because it is in group 7. And then we're going to have a second fluorine. And these are floating around in the gaseous state, and they see each other and they go, oh, look, if we share electrons, we're each going to have a full octet. So they come together and they share a pair of electrons. All right, let's draw the Venn diagram. Verify they meet the octet rule. Okay, first fluorine met the octet rule. Second fluorine met the octet rule. They both think they've got 8 electrons. Everybody's happy. Let's take a look at H2O. So we have a hydrogen atom, 1 electron. We have oxygen. Now remember that oxygen has 6 valence electrons. And then we have another hydrogen. So these atoms are going to get together so that everybody has a full valence shell. Remember, with hydrogen, that is 2. So we're going to share a pair of electrons between each oxygen and hydrogen. And if we draw the Venn diagram, notice that each atom meets the octet rule. So in order to meet the octet rule, or the duet rule if you're hydrogen, the atoms are going to be sharing electrons. And it's especially important to note that they share pairs of electrons. Now we're going to look at sharing some more pairs of electrons, and we're going to introduce a new term here, lone pairs of electrons. So lone pairs are electrons not shared between atoms. We're going to find out in Unit 6 that they are very important in controlling the shapes of molecules. We're going to look at some examples of lone pairs. Along the way, we're going to learn to count the number of valence electrons in a molecule, because you're going to need that for the next part. So we're going to go through these examples of finding lone pairs. So our first one is HCl. So let's first count the number of valence electrons. Hydrogen has 1 plus 7. So let me write this, hydrogen and chlorine, for a total of 8 valence electrons. This is not the total electrons. It is just the valence electrons. We look at our structure here. We have 2, 4, 6, 8, someone right here. We have 8 valence electrons. Each atom has met the octet rule, and I'm going to circle the lone pairs. So we have 2 lone pairs. Let's look at H2S. We're going to count the valence electrons. So we have 2 hydrogens and 1 sulfur. So that is 2 times 1 plus 6 for a total of 8. So we have 8 valence electrons. And there is our dot structure for H2S. Oh, you know what? I didn't do this one right. Circle that, and this should be a 3. I can't count. That's 3 lone pairs. Sorry about that. 3 lone pairs for the HCl. All right, so for H2S, we have 2 lone pairs. Let's look at NH3 and CH4. So NH3, we have 5 from the nitrogen plus 3 times 1 from the 3 hydrogens for a total of 8 valence electrons. There's our dot structure for NH3. We have 1 lone pair. So this is ammonia. It's what stinks in windshield cleaner or window cleaner. All right, our last one is CH4. Carbon has 4 valence electrons. Hydrogen has 1, but there's 4 of them. So 4 plus 4 times 1, 8 valence electrons. And there's our dot structure. CH4 is methane. So there's our dot structure for methane. We have 0 lone pairs. Okay, so we've talked about single bonds and lone pairs. Now we're going to talk about double bonds and triple bonds. So double bonds share 2 pairs of electrons. So let's take a look at oxygen. First, we're going to count how many valence electrons we have. So we have 2 oxygens times 6 for a total of 12 valence electrons. So somehow the oxygens have to share their atoms in such a way that they each end up with 8. So let's draw the dot structures. Okay, so these 2 electrons are going to be shared, and these 2 electrons are going to be shared. So we end up with 2 shared pairs of electrons. And then we've got 2 lone pairs. If we draw the Venn diagram, each oxygen gets to count all the electrons that are shared. So each has met the octet rule. Now I want to draw your attention to one little thing about the oxygen atom. Notice that I left these electrons paired, okay? So one of the rules about molecules is always use pairs of valence electrons in molecules. Everything moves in pairs. So always use pairs of valence electrons in molecules. Never leave an electron by itself. It wants to be in pairs. So that's double bonds. Notice that oxygen is one of your diatomics. Now we're going to do triple bonds. And in this case, we're going to share 3 pairs of electrons. So let's take a look at nitrogen. We're going to count the valence electrons. We have 2 nitrogen. Each nitrogen has 5 valence electrons. That's a total of 10 valence electrons. So somehow 2 nitrogen atoms have to share enough valence electrons that in the molecule they end up with a full octet. So there's the dot diagrams of the elements. So we're going to share, 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 share. And we end up with 3 shared pairs of electrons. So there's our dot diagram for nitrogen. Notice that each nitrogen meets the octet rule because each nitrogen gets to count all the electrons that are shared to the center. So what we're going to look at next is drawing molecules and replacing all those dots with some lines because things get very, very confusing looking. So we're going to replace pairs of bonding electrons with dashes. We're going to keep the double dots for a lone pair or an unshared pair of electrons. We're going to represent a single bond by a dash. So, for example, down here with HCl, this is going to become HCl. Okay, so we replace a shared pair of electrons with a dash. If we have a double bond, we're going to use 2 dashes. So down here, O2 becomes this. And then for a triple bond, we're going to have 3 dashes. So nitrogen is drawn like this. Okay, we're going to stop there before we go on to the really complicated part, which is drawing Lewis structures of molecular compounds.